right, let's go and review some things we've been talking about in our last several lessons. You have your homework out, page 204, problems 4 through 6. We've been working with movement about an axis. And we said in general, any movement about an axis can be called class angular movement, right? Angular motion. If the axis is external to the object being described, then the object going around the axis is in a sense orbiting that external axis. We would refer to that class as circular motion. That's not the topic of this chapter necessarily, though if an object is spinning like a merry-go-round and you are on the merry-go-round, you are technically in circular motion while the merry-go-round upon which you stand, right before you fly off, is spinning about its own internal axis. So there's definitely a correlation between the circular and the movement about its own internal axis class, which we call rotary motion. But rotary motion is the primary point of emphasis in this chapter. And we said that as an object turns, yes, a speck or any point on the rotating body is in circular motion, but the body itself, as it rotates, isn't moving from one place necessarily to another. Right? The merry-go-round stays still, but it turns, so its displacement is not linear, but rather angular. It turns, and that angular displacement we represent not with the letter D, class, but with, you go Greek here a lot.
Omega, no.
Theta rad, because remember it's an angle that is displaced, right? It's an angle that is turned rather than movement from one point to another. It's a change of position from one angle to another. So theta rad. And we said one way in which you could find the amount of displacement would be to look at any point along the rim of the object and measure from one point to the next point along that curve or along that arc, and you could compare the arc length to the radius. And so theta rad, we said, is equal to S over R. If the arc length equals the radius, that angle will be called the central angle of a circle for which the arc length equals the radius. Is how we define 1 radian. 1 radian. And we'll use radians, hence the rad notation here, theta sub rad. Okay, the rad here is to remind you we need radians for our angle of displacement because it's unitless, right? Whatever unit, inches, feet, centimeters, whatever for the arc length, cancels with the inches, feet, centimeters, whatever for the radius. When you can, cancel those out, you get unitless radian measured. We said that as an object is spinning, an object could spin fast, an object could spin slow. We would then be referring to the object's spin rate, or we call it angular velocity, the speed of the spin, the angular velocity represented by the Greek letter omega. And maybe that's one of the things that makes this section a little harder is the use of the Greek symbols. It's a little different for us. But omega used to represent angular velocity, and velocity is normally distance over time, or displacement over time. Well, there's not a linear distance now, it's a spinning displacement, so omega would equal theta rad over t, the angular displacement divided by time, giving us radians per second, or just per second, since radians are technically unitless. If an object starts spinning faster, 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 we would say that the object is accelerating, though it's not an acceleration from one point to another, but rather it's an increase in the spin rate. We would call it angular acceleration. So it's angular displacement, angular velocity, angular acceleration, represented by the Greek letter alpha, which at least, that's close to an A, right? It's the Greek equivalent. So that one might be a little easier to remember than the theta rad and the omega. But we said if we wanted to find the angular acceleration, we would use what formula? Well, it's omega over t. Omega sub f minus omega sub I over t. The change in the angular acceleration, final minus initial, over time. And so here's our radians per second per another second, or radians per second squared, our unit for angular acceleration. We had a couple other equations as well that we used for this chapter. They were based off of, just as these are based off of v equals d over t and a equals v sub f minus v sub I over t. A couple other equations. Can you give me one of those? those volunteered? See, I think I know one of the others. Kendall, I saw your hand move. Go ahead.
Theta red equals
Omega.
Yeah. Sub F. So I. Yep. Squared. Yep.
How about T?
Yep. Plus 1/2 omega. Nope. Alpha.
T squared. Okay, so we need to work on memorizing these over the weekend, don't we? Spend some time this weekend working on memorizing these. It's the equivalent of D equals V sub I T plus 1/2 AT squared. But that was always a harder one to remember in the first place. Maybe a little bit easier one to remember might be the one that has some squared omegas in it. Either of you want to take a shot at that? Michael's moving his hands. Go ahead, Michael.
Omega sub F squared equals omega sub I squared minus plus 2 theta red, alpha.
Plus 2 alpha theta rad. V sub F squared equals V sub I squared plus 2 AD. And again, we're just making those substitutions. So this is our lineup so far of equations that we need to have memorized. The thing is, though, it's always theta rad, theta rad, theta rad, theta rad. We can have radians, radians, radians. We can't have degrees. So if we have degrees, we need to change them into radians. How will I do that, Audrey?
Multiply by pi over 180.
I'm going to multiply by pi over 180 degrees so that the degree symbol cancels. If we were given a pretty common unit, revolutions, right? Because let's be honest, measuring things in how many full turns it does, that's just easy, right? Like, how many times does the Ferris wheel go around? Count how many times that loved one passes you, right? Whatever, right? It's easy to count revolutions unless it's super fast. Radians is harder. How do I go from revolutions to radians, anyone? Multiply by 2 pi because it's 2 pi radians in every single revolution. A common unit, by the way, that will be given is revolutions per minute, RPM, in which case we need to change the revolutions into those radians and then change minutes into seconds, so we have radians per second for our omega value. Then at the end of the hour yesterday, we began just talking about this. Remember, the merry-go-round is spinning, right? The green balloon just fell, by the way. There are 2 balloons in the back and sticking to the ceiling by static cling, electromagnetic attraction, and, the electric attraction, I guess, technically. And a greenish balloon and a blue balloon, and Ms. Morse asked us to tell which one fell first, in case you're wondering. Green balloon just fell. It was at about 7:35 mark, so we'll keep an eye on the blue balloon and see when it goes down. Anyway, so yesterday we was talking about the correlation between that which is linear and that which is angular. If you're standing on a merry-go-round and the merry-go-round starts spinning faster, you will start moving faster also. Your forward progression, you're not spinning, you're going around and round, but you're not spinning, it's spinning, you're on it. At least as long as you can stand it. And so you're going around, you're going to go faster, right? If it spins further, if it spins a little bit, you move a little bit. If it spins further, you move further, right? If it begins to speed up, you will speed up. So there's definitely a correlation between that which is linear and that which is angular. And I gave you 3 formulas, and I said, I don't want you to memorize these. I want you to memorize one easy rule instead. So, Michael, do we remember the one easy rule? You're nodding your head. Oh, he just remembers that I said to memorize one easy rule. All right. One of you ladies remember what the rule is.
Linear equals angular times velocity. No, times something.
Radius. The radius is the key that connects them all, right? The radius times whatever the angular displacement, acceleration, velocity is going to give you the linear displacement, velocity, or acceleration. So linear equals angular times radius. Say that with me, class? Linear equals angular times radius. I said say it with me, that I didn't say. Can't follow my own directions. Let's try that again. Linear equals angular times radius. Now, that means if you know the angular and you want the linear, times radius. What if you knew the linear, but you wanted the angular? You have to divide the radius, right? Normally, though, we'll see it the other way around. All right, so memorize that fact instead of equations. You had to use this on problem number 6, by the way. Well, let's start with problem number 4 from your homework now. Read the problem, if you would, Kendall.
Starting from S, 0 flywheel of a steam engine acquires a speed of 4.5 radians per second in exactly 1 minute. Find the angular acceleration in radians per second squared.
Well, let's write down all the numbers that we were given.
The initial.
Initial what?
The initial start. The omega sub I.
Good, the speed, the spin speed, the omega sub I, the initial angular velocity
Is 0.
is 0 because it's starting from rest. 0 radians per second starting out. But
The final velocity is 4.50
radians per second. All right, so the final angular velocity, omega sub F, 4.50 radians per second. The other number they give us?
is time.
Time, okay?
Is 60 seconds.
They say 1 minute, but we know that's going to be 60 seconds. Now, by the way, how many sig figs in 60 seconds? Infinite, right? Because that's the definition of a minute is 60 seconds. So this is not affecting my significance at all. This is the only number, the 4.50. Also, rest is infinitely significant, 0. So I'm going to have 3 sig figs in my answer, and it asks us to find what, Kendall?
Find the angular acceleration.
And what equation did we need to use to find this?
Alpha equals omega sub F minus omega sub I over 2.
There we go, and it's as easy as plugging in the numbers, especially since omega sub I is 0. So it's 4.5 divided by 60. And that's not hard, 4.5 divided by 60. The number's a little small, but not bad. Oddly enough, though, I do want 3 sig figs. My calculator doesn't have 3 right now. How should we write the answer, Kendall?
I had 0.075.
That's what my calculator has too, but technically, how many sig figs is that, class? 2, because remember, this 0 is not significant. Slap an extra 0 on the end, 0.0750 or 7.50 e negative 2, though this is probably still easier to write. And acceleration, angular acceleration, rather, measured in
Radians per second squared.
radians per second squared. There's our answer. How many have that for number 4? Question, Michael.
I ended up mixing number 4 and number 3 together.
Oh, that's a shame. Okay. Kendall, other than sig figs, you had it?
Oh, yeah.
Okay. All right, questions. All right, number 5. Go ahead and read that if you would for us, Audrey.
An automobile engine is idling at 30.0 radians per second. Upon acceleration, it reaches a speed of 300 radians per second in 2.00 seconds. Calculate A, the angular acceleration, and B, the angular displacement during the acceleration.
All right, good. So radians per second, again, it takes 2 pi radians. That's about a little over 6 radians to make a revolution. So 30 radians per second is going to be about 5-ish, not quite 5, revolutions per second. 60 seconds being a minute. It's about 300 revolutions per minute. So this is the tachometer on the car dropping down like below the 1, right, when you're just sitting at the stoplight. But then the light turns on, the race is on, hit the gas pedal, and obviously the tachometer along with the speedometer goes up, and it goes up to 300 radians per second. Again, that's going to be about 50 revolutions, 45-ish revolutions per second. Take that out to a minute, and that's going to be, a couple thousand. So you're still getting decent gas mileage. You're doing okay there. You're not gunning it, really. It takes 2 seconds to get up to that rate of revolution, if you will. So the first number I need to write down.
The initial omega is
Angular velocity.
equals 30 radians per second, 0.0.
30.0 radians per second, okay? And the next number?
The final angular velocity.
Good. Omega sub F is?
Equals 300 radians per second.
So I'm feeling 3 sig figs here. The next number?
The time is 2.00 seconds.
And first of all, just like the last problem, so it's really not much different. They ask for the
Acceleration.
Angular acceleration. And so again, to solve the equation, we're going to use what formula?
Omega sub I, omega sub F minus omega sub I over T.
There we go, omega sub F minus omega sub I over T. The difference is this time, you can't cross out the omega sub I because there is a value there. So we do it in our head, 300 minus 30, 270. I bet we could finish it in our head. Divided by 2.
135.
Yeah, it comes out to 135. That's already the 3 sig figs I want, so we didn't even need a calculator so far. And of course, angular acceleration in
Radians per second squared.
So there's my first answer. It's not even rounded. It came out evenly for me. Did we get the 135 radians per second squared? But then it goes further this time, unlike the last problem. And number 5, it also asks us to find, Audrey,
the angular displacement during the acceleration.
the angular acceleration when or the angular displacement rather, while all this was going on. How many spins were there, right? And of course, that's not asking it in revolutions. That's actually what we would say is a spin. A spin is a revolution. We're going to get it in radians. What equation, looking at what I've got here, might I use to find theta rad?
Omega sub I times T plus 1/2 alpha T sub.
There we go. This is probably the best one to use. It's most direct. Now, technically, you could use this equation if you subtracted the omega sub I squared, divided away the 2a. But this one, we don't have to really manipulate at all. So we're going to take the 30 omega sub I times 2, plus a half, alpha is 135, and then t squared we can do in our head class. 4. Well, hey now, half of 4 is 2. 2 times 135 is 270, and 2 times 30 is 60. We can add those together to get. Apparently in 2 seconds it makes 330 point radians. What if I wanted revolutions? I want to know how many complete spins. You divide by 2 and divide by pi. I'm just curious for my own sake here. And that would be about 52.5 total revolutions in 2 seconds. Questions on the second part. How many got the 330 point radians? Excellent. Questions on problem 5. All right, problem 6. Go ahead and read that for us if you would, Michael.
A CD player rotates a CD at a speed of 420 radians per second. What is the linear speed of a point on the CD at 1 centimeter and at 3.5 centimeters from the CD axis?
The linear speed. Ooh, how do I find linear, class? Angular times radius. Well, they gave me the angular, right? They said that this particular CD player is spinning the CD at 420 radians per second. That's the angular velocity. We want the linear velocity or linear speed if the point is 1 centimeter from the CD axis. So our radius is 1 centimeter. Well, if we multiply angular times radius, class, we get 420 centimeters per second. Oh, yeah. So that's okay. We could change it into meters by just moving the decimal
Left twice.
2 places. 4.2 meters per second. Still really fast for a point spinning on a CD. Questions on that? And then it says, well, what if part B? What if the radius is 3.5 centimeters? Well, let's go ahead and change it to meters up front, class. 0.035 meters. And then the second answer would give us that one we can't do in our head. At least I can't do it in my head. Or at least I don't want to do it in my head. Michael?
14.7.
14.7 meters per second. So there's the 2 answers for part A and part B. Obviously, the point that's closer to the axis is not spinning as fast. The point that's further out will be spinning that much faster. Questions on problem 6? Do we get those answers on number 6?
You just have the decimal wrong.
Okay, so you did the centimeters per second. Okay, questions? All right. Now, with an object that is spinning, if another object attempted to stick to that one, that object then would be going in circles, wouldn't it? Whether it's an object like a small child sitting on the merry-go-round with a little safety belt thingy and holding onto the pole, they're going around in circles because their legs are holding them on, their hands are holding them on. A stone that gets wedged in a tire. There's the grip, the friction of the tire treads holding that rock. A piece of gum that gets splattered on the side of a tire or something. It's going around and around because of its own adhesiveness, right? Whatever. If an object is spinning and another object adheres to that in some way, the force required to keep it going in that circle, we call force required. Well, that might be, but in general, any force required to keep an object moving in a circular path. Centripetal force. And we're familiar with centripetal force from earlier, right? We said centripetal force back before semester break was F sub c equals mv squared over r, right? Well, v, though, is the linear velocity of the object that's spinning, right? Of the object, that is on the spinning object. That's the forward progression of the piece of gum or the rock or the kid on the merry-go-round, right? But what about from the spinning object's perspective? Well, we wouldn't want the linear speed, but rather the rotating speed, correct? How is linear related to angular, class? Linear equals angular times radius. So a linear velocity could be replaced with angular times radius, correct? Well, if you're going to take a v squared or an r omega squared, you realize that means each of these needs to be squared. So we could say that f sub c equals m r squared omega squared over r, but just looking right here, thoughts on what we could do to simplify that? Cancel one of the r's. Take an m r to the first omega squared, and that's the next equation for you to write down. Centripetal force involved on a spinning body is going to be m r omega squared. And that looks at it from the perspective of the spinning body, the spin rate, m r omega squared. Now, obviously, centripetal acceleration, force is mass times acceleration. Here's the mass. Apparently, the r omega squared is the centripetal acceleration. So a couple of other equations. Now that we understand how linear and angular are connected, we can extrapolate out not really new, but different looking formulas for centripetal force and centripetal acceleration. Once you have that copied down, turn to page 192. Flip back to page 192 and look at the example problem. And Michael, if you'll go and read the example problem at the top of page 192.
An automobile tire has a diameter of 60 centimeters. The tire is rotating at a rate of 89.4 radians per second when a car is driving down the highway. Find the speed of the vehicle, the centripetal acceleration of a point on the rim of the tire, and the centripetal force on a 12-gram stone embedded in the tread.
All right. So one thing at a time here. The first number they give us, Michael,
Diameter
is
0.6 meters.
0.60 meters, 60 centimeters. I like that you converted. But do I ever really use diameter for anything? No. I use radius. So we'll say 0.30 meters. The next number we're given, Audrey.
The 89.4 radians per second.
What is that?
Angular velocity.
That's the angular velocity of the tire. Let's see. Oh, that's all they give us. And it asks letter A for the speed of the vehicle. Speed of the vehicle? What makes a vehicle go faster? Oh, the blue balloon fell. I didn't actually see it fall. I just noticed it's on the floor at 23 minutes. Not sure when it fell. Oh well. Speed of the vehicle. What determines how fast a car can go? How fast the wheels spin, right? Faster the wheel, assuming you have traction, right? But the faster the wheels spin, the faster the vehicle's going to go, right? Linear velocity of the vehicle is dependent on the angular velocity of the tire. How do I find linear if I know angular? Okay, we should have this a lot more confident than this. We sound a little tentative still, class. Linear equals angular times radius. So if I want the linear speed of any point on the rim of the wheel, that will also be the speed of the vehicle. V equals r omega. And so I'm just going to multiply the 0.3 meter radius of the tire, which is 1 foot, by the way, approximately, and times the 89.4 radians per second. How fast is the vehicle going? And not radians per second now, but meters times radians per second. But remember, radians are technically unitless, so it's just meters per second. Not meter radians or anything like that. Radian is just a concept to help us visualize. So meters per second. We could round that off, of course. I think it's 3 sig figs. Yeah, so round it off, class. All right, part B, because it keeps going. The centripetal acceleration on a point on the rim of the tire? Well, how do I find centripetal acceleration? Anyone?
R omega squared.
Either R omega squared or V squared over R. This was the old definition. Now, the downside of this is you rely upon having done this correctly. I'm not real likely to screw that up. Okay, so I'd probably get it right. Or we could say, forget this one, we can go with R omega squared now instead of V squared over R. Either one would work, but R omega squared means I square the, and then multiply that answer by the R, which is 0.3. And what is the centripetal acceleration?
2,397.7.
Okay, round it off.
2.4.
Yeah, 2,400 is great, but there's only two sig figs. We have to go scientific notation. 2.40 E3. And acceleration is measured in meters per second squared. Again, this isn't the angular acceleration. This is centripetal acceleration. 2.40 E3 meters per second squared. Part C says to find the force, centripetal force, on a 12-gram stone that's embedded in the tread. Well, 12 grams, of course, is mass, but I'll need to change that. 0.012 kilograms. Now, there's three formulas I can use for this. Mass times acceleration, and V squared over R, or mR omega squared. I like the first one. Assuming I still have this number on my calculator, just multiply this number by the mass. And how much centripetal force acts on this stone wedged into the tire? How much friction is holding it in there? Friction and, I guess, an applied force of the rubber probably gripping the sides as well. It's not just friction.
27.
Rounded off to 28.8 newtons of centripetal force holding it there. Keeping it going round and round. Questions on that problem? Do we see how the linear is related to the angular and how we could still use linear, right, if we wanted to, with centripetal force and acceleration, or we could convert over to the angular? It's really kind of up to you. Questions on this? Flip back to page 204 then. Flip back to page 204. And look at problem number 7. Read that for us if you would, Kendall.
Okay, so problem 3 has a radius of 5.10 meters. After the wheel attains a constant angular speed of 0.35 radians per second, calculate the wave speed, the centripetal acceleration, and the centripetal force on a passenger weighing 625 meters.
All right. At your seats. Go ahead and work this problem. Consider it temptation. did. What's another name for rim speed? Linear velocity. Check your first answer. Did you do angular times radius to get 1.79 meters per second? All right, keep working. All right, two ways to find centripetal acceleration. The old way, v squared over r, take the v that was on the calculator, well, technically this one, not the rounded value, square it, divide by the radius, or r omega squared, that would have worked as well. Did we get 0.625 meters per second squared? No. Question?
0.0625.
So we square the 0.35, check your calculator again, and then multiply by 5.10. I'm wondering if you multiply by 0.5.
So I did 0.350 squared.
Right, you square that, and then multiply by 5.1. Got it now? All right. And then for centripetal force, since I have the acceleration already, just multiplying by the mass would be the easy way. You could do mr omega squared or even mv squared over r. There's just one problem. I don't know the mass. They told me the weight, right? The force of weight instead. So how do I get mass? Going back to last semester. Divide out gravity, right? So we'll take the 625, divide out the 9.80, and we'll get an approximate mass of that. We can take that value times our centripetal acceleration, assuming we have that correct, and we'll get about how much force. 39.8 newtons of centripetal force holding them in place. All right, questions on problem number 7? Questions on that? All right, if you're watching on YouTube, you'll see 2 links in the description of the video. The first one is for a classwork handout. So you'll want to bring that handout up, pause the video while you get that handout, either brought up on your screen or printed out. It might be easier to work. I've already handed it out to students in this classroom. So let's have, let's see. Audrey, go ahead and read the first problem for us.
A young boy goes into a revolving door and can't figure out how to get out. He stands paralyzed with indecision, exactly 1.3 meters from the center of the door for 1 minute until his mom comes to his rescue. If the door makes one full revolution every 3 seconds, determine 1, his angular displacement, 2, his angular velocity, 3, his linear displacement or arc length, and 4, his linear velocity.
Okay, now 3 and 4 are going to be really easy because 3 and 4 ask us to find class linear something. And anytime I'm asked for linear, that's easy. All I got to do is multiply radius times angular, right? So if I find angular displacement for number 1, number 3 is a piece of cake, just multiply by the radius. Number 2, I find his angular velocity, linear velocity is a piece of cake for number 4, just multiply by the radius. So the real key is getting 1 and 2. Take a moment at your seats to work these. To help you out, I underlined the 3 things that you need to be given. The radius, distance from the center, time, 60 seconds, and technically a revolution every 3 seconds is telling you how fast the door is spinning. So this is the angular velocity. It's just not in the right terms. But a revolution every 3 seconds, that's your spin rate. But we don't want revolutions per 3 seconds, we want radians per 1 second, right? So instead of revolution, and go ahead and simplify it down. And this is actually the answer to part 2, is angular velocity. What do we get?
2.094.
You might want to put that in the memory of your calculator. It's 2 sig figs, isn't it? 2.094. There's 2 different ways to get part 1, because we kind of skipped over part 1 because we were already getting part 2. How do you define it as angular? Well, first of all, how do I represent angular displacement, class? Two ways I could find the theta rad in this problem. Call out ideas.
S over R.
Okay, S over R is an option. Do I know the S?
No.
No. But it would have worked if I'd known those 2 numbers.
Yeah. Could you do omega equals theta rad over t?
You could use omega equals theta rad over t and cross multiply. And what do we get?
1.36.
125.
I got 125.66 or rounded 2 sig figs, I guess 130 radians. There's 2 other ways you could do it. Another way would be theta rad equals omega sub I t plus 1/2 alpha t squared. You're like, well, wait a second, Mr. Dasky, I don't know what omega sub I. Well, omega sub, it's the same spin rate for that revolving door the whole time. We would assume. It doesn't say it's any different. So omega is the omega sub I. Well, Mr. Dasky doesn't give me an acceleration. Well, that's because we assume the door is spinning at a relatively constant rate. And you see it's actually the same equation. We just look at it from a different perspective. There's a fourth way that we could try to find this. Every 3 seconds, it makes a revolution, right? How long was he stuck in the door?
A minute.
60 seconds, a minute. How many sets of 3 is that? And it makes a full spin every 3 seconds, right? So it would be 20 trips around, right? Be very dizzy. 20 revolutions. And then all I'd have to do is multiply it by 2 pi, because every revolution is 2 pi. And we could have done that. That would also get us to 130 rounded, 125.66. So any of those ways would work. Questions on the first 2 parts. Now for the easy stuff. Number 3. It wants the linear displacement. How do we represent linear displacement?
Meters.
Well, we're going to use meters for our unit. How do we usually represent displacement?
The theta rad. No.
That's angular displacement is theta rad. Linear displacement. From me to you.
D.
D, right? D for displacement. Though it's not from me to you, it's round and round and round in a circular path. Well, if instead of a straight line path, I curve that path along a circle, we now call that distance an arc length, don't we? You could say D for displacement, you could say S for arc length, which it technically is. I don't really care. The linear displacement is always going to be equal to
Angular times radius.
angular, which we just found, we still have it on the calculator maybe, times radius. How far does that boy travel? Along a very tight circular path.
2.7.
Ooh, angular times radius.
About 160.
About 163.36, blah, blah, blah. Rounded 160 meters he travels. More than a football field and a half, all in a rather tight circle and stuck in a revolving door. No wonder he's dizzy when he gets off. All right. Questions on that part? The omega was the 125.66 blah, 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 or 20 times 2 pi. Multiply that by the radius of 1.3. Number 4 asks us to find the linear velocity. How do we represent linear velocity?
A.
That's acceleration. V, velocity, right? V. How do I find linear velocity? Class?
Angular velocity times radius.
Angular times radius. Well, we know the angular velocity. It's hopefully still in the memory of your calculator, the 2.094 blah, blah, blah. Multiply that by the radius. And how fast is he actually moving?
3.5.
Ooh, that's not what I got.
2.7.
Remember, you're multiplying by 1.3. So this memory value times 1.3. I got 2.722, blah, 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 rounded off. 2.7 meters per second, which is a slow walking rate. So he's not actually going that fast forward, but the spin is what's causing the dizziness. Questions on this first box? Do we see how to just kind of solve the pieces, piece at a time? There's more than one way to do things a lot of times. Right, if the first thing you saw was, bam, a revolution every 3 seconds, he's stuck in there for 60, that's 20 revolutions. You could have gotten part 1 right away. Then you could have used part 1, divide by time, to get the omega. You could have done it that opposite direction. That would have worked too. And once you know angular, to find linear, multiply by radius. Go to box number 2. And read that for us, if you would. Let's see. Audrey read the last one. Kendall, read this one.
A bicycle or rounded determines distance and speed based on the speed and number of revolutions of a bicycle wheel. If a 24-inch diameter wheel makes 1 revolution every 0.183 seconds, determine the angular velocity of the bicycle and the linear velocity.
All right, first number they give us, class. 24. That's the. I don't care about that, do I? So I'll go with
12 inches.
radius is. Do I want inches? Probably not. Let's make that. Ah, I love that number 1. Such an easy number to use. So my radius is basically a foot, which is why I picked a 24-inch bicycle wheel. All right, so I could use 1 because I'm not lazy. All right, let's see, the next number it tells us.
Time is 1.83 seconds.
Well, that's the time for every revolution, right? So when it gives you revolution in 0.183 seconds, I guess we could technically say times 0.183 seconds, and the revolution then would be the what? The displacement, right? The angle of displacement is 1 revolution, or rather, you could think of it that way. I was going to think of it like I did over here, where I said a revolution every 3.0 seconds, and I called that omega. I was going to do that. Just call it, but technically, I mean, omega over time is what we're doing anyway to find, or theta rad over t is what we're doing to find omega. So the 2 pi radians over the 0.183 seconds. And what is the angular velocity? And that's 3 sig figs or 2 sig figs? It's 2 sig figs. Well, no, wait. I didn't use this 2 sig fig number up here. I only used a 3 sig fig number, so it is 3 sig figs. 34.3 radians per second. And then it says determine the linear velocity. How do I find linear velocity?
Angular times radius.
Good, the angular that's already on my calculator times the radius, but the radius is a foot. So if you multiply by 1, you're going to get same thing. Though the 24 inches, 12 inches, 1 foot, that's 2 sig figs. So instead of 34.3, I'm going to say, 34. And it's not radians per second now, but feet per second. Questions on the second box? Let's go to the third box, which builds on that other one. It says he's maintained a constant speed for 10 minutes. Well, now, class, that's my new time. 10 minutes? Anyone got an issue with that?
600.
Yeah, 600 seconds. 2 sig figs, though, from the 10 point, right? 600 seconds. And it says find his angular displacement. So, find theta rad. Stay with me. How am I to find theta rad? Omega times time, right? I have the omega hopefully still on my calculator. I didn't clear it, 34.33, it's still there. I have the omega on the calculator, multiply that by 600 seconds. Since omega equals theta rad over t, theta rad equals omega t, wow. 20,600, which 2 sig figs from the 10 point minutes. So we're going to have to say 2.1 E4 theta rad. Rad, maybe it's right, 2.1 E4 radians. That's his angular displacement. Nobody cares when they go on a bike ride what their angular displacement is, but that's technically what anyone ever used an odometer on a bicycle? The little sensor that goes around and around? Yeah, I had one. What it's tracking is how many revolutions you make. But what it tells you, it does all the calculations for you to tell you the linear displacement, the distance that you actually travel. And to find linear, angular times radius. Now technically it's the arc length, but again, the arc of the wheel is being spread out, if you will, over the distance multiple times. And so multiply that by a foot, what do you got? 2.184 feet. Which, if you wanted miles, you could divide that by 5,280. You get about 3.9 miles for that bike ride. You're going to finish this last problem for homework. And I also have another handout. I was hoping to finish the whole handout in class today. Didn't quite get to it. Shorter handout, though, for homework. So finish the last problem on the classwork handout and do the homework handout for homework this evening. We're going to take a look at this on Monday. And then we're going to take a quiz. We're a little shaky on formulas. This weekend, shore up formulas. A few terms here and there to know as well, but especially formulas, get units, get shored up on those things. Next lesson on Monday, we will go over this, review, take a quiz as we wrap up section 13.1. All right, have a wonderful rest of your day. Have a wonderful weekend. You are dismissed.